Okay, now let me share my screen. Okay, can you see the screen now? Yeah. Just turn on your mic and say yes, because I won't be able to see the Zoom window.
Yes, sir.
Yes.
Okay, thank you. Okay, so good evening, good evening, everyone. Assalamualaikum warahmatullahi wabarakatuh. And first of all, let me introduce myself. My name is Jason Alexander Yusuf, and I'm from Chemical Engineering Department, International Program, Batch 2021. And tonight I'll be giving you the assistance for your basic chemistry course. And for tonight's discussion, we will have 5 different topics, which is stoichiometry, chemical equilibrium, acids and bases, reactions of metals, and electrochemistry. Okay, so these are the subtopics that we will discuss in each part of the assistance, and hopefully you will be able to understand what's being taught tonight, and you can use this knowledge to excel in next week's midterm exam. Okay, so let's begin. I think I'll just turn on my cam. Okay, so first off, it's the stoichiometry problem. And guys, for this one, for each chapter here, we'll discuss 2 different problems for each. Okay, so hopefully by 9 we'll be able to finish, so that you can rest or do whatever you have to do. And so this is for problem 1. Let's read the problem first, where we have 0.24 grams of compound A vapor, which is passed over copper to oxide, CuO. And this compound A, even though the problem doesn't say so, you should already somehow get an idea that it's an organic compound, right? And the products that are collected, it is found that it contains these products. And so for this, let's start with the calculations. So first, we need to determine the mass of carbon present in the compound. And let me just zoom this in. Oh, wait, give me okay, here. So basically here, you are asked to find the mass of carbon present in this amount of CO2. So what you have to do is take the mass and then we perform the ratio analysis, which is where we will multiply the mass with the AR value and the MR value of CO2. So basically, let me give you the data first. So AR of H is 1, AR of C is 12, Ivana, I'll hand over the docs to, I think, my mentee from this one or from somebody else. I'll send it in the chat later once we're done with the assistance. Okay. Oh, and guys, if you have any questions, it's okay. Don't be afraid. Just interject me at any point during the assistance. Okay. Okay. As I was saying before, this is the data that we're going to use, and this is the AR of oxygens is 16. Okay, so now we're going to do the calculations, which is the AR of C plus 2 times the AR of O, and for the numerator we have the AR of C. So that means this is 0.352 times 12 over 12 plus 32, that's 44, and you will get a value of, I have not calculated it, give me a moment. you will get a value of 0.096. So that's the amount of carbon present. So first let me just how do I change? Give me a moment. Let me just so that you can see clearly. Give me a moment. They will I give this. Okay. So for this, for the question B, we do the exact same procedure that we do in A, and we do this. Um, and so we will get this. AR of H is 1 over 2 times AR of H, that's 2 plus AR of oxygen, that's 16. So that would be 1 over 18, and you will get 0.008, right? And so what we're going to do next is we're going to calculate the mass of oxygen present by using the mass of the carbon dioxide as well as the mass of water. And so for this one, we're going to do O at CO2, that would be 0.352 minus 0.096. That would be 0.0256. And the O at H2O would be 0.144 minus 0.08. That this is a 0. Okay. 0.008. That would be 0.136. Oh, sorry, there's an error here that I just noticed. This one should be 0.256. So sorry about that. Okay, and so the total mass would be and so this value would be, all we have to do is just add these two and we will get 0.392. Okay, so now let me just create more space. And yep. And actually, I forgot to mention that we want the values in mole. So, but don't worry, we're going to do that in the second part in here. And so, for the recording, yes, we'll share the recording as well. In I think Rayan can clarify if it's false. You can view the recording in IMPI's YouTube channel. So don't worry about it. And we're going to now next, as I was saying, we're going to use the value of the moles, which is 0.096 divided by 12. So that's the mole. This is since we want to find the mole first. Next would be 0.08. Okay, sorry, this one there's an error here. It's supposed to be 2. So sorry about that. Let me recalculate. 0.016. Sorry about that. Zero 16. Since this is 0.0128. Okay, then final value will change. Zero 0.384. Right. Okay. As I was saying just now, let's go back here. This is 0.6 divided by 1 equals to 0.384 divided by 16. So this will be your mole ratio. And next, we're going to solve this part here. And for the first part, which is 0.096 divided by 12, we're going to get 0.008. For the second part, it's 0.016. I'll just write this here, CHO, so that you won't forget. And next, it will be 0.384 divided by 16. That will be 0.024. Okay, so for the next step, we're going to divide this entire thing by the smallest value. And if you take a look here, the smallest value is 0.08. So we divide this thing by 0.008. So you will get 1, 2, and 4. Sorry, 3, not 4. And so your empirical formula would be CH2O3. Okay. Until here, is there any question? No? Going once, going twice, no question. Okay, I'll continue. Okay. For this one, it's about the ideal gas equation to get the MR. So first of all, let's write down the ideal gas equation is PV equals to nRT. Right? This is the ideal gas equation, and in which P is your pressure, V is your volume, N is your number of moles, R is a constant known as the universal gas constant, which is R equals 8.31 or 314 joules per mole Kelvin. And basically, if you can go through any resources that you want, they'll also provide values like 0.082 liter ATM per mole Kelvin. But usually we're going to use this as the basis, as the value. Okay, so next is at the pressure of 100. We want to find the MR of A. And remember that the formula of mole N is the mass divided by the MR. And so we can substitute this formula here to get M over MR RT. Now, to get MR, we just substitute MR with PV, and this is what we'll get. And from the previous question, we know the mass of M, which is 0.24. We know the pressure, 110 kPa. We need to convert it to Pascal first by multiplying it to 1,000. Next, we also know the volume, which is 67.7 centimeter cube. However, we need to convert that to meter cube. So we multiply that with 10 to the power of negative 6. And we know the universal gas constant is 8.31. For this one, for this time, I'm going to use 8.31. If you want to use 8.314, go ahead. And for the temperature, it's at 60 degrees Celsius, right? And so, but then for 60 degrees Celsius, we need to first convert it to Kelvin. So in order to do that, we at 60 with 273. And so this one we will get 333 Kelvin, right? So this is 333. Oh, and sorry, there's a slight error here. The mass is not 0.24, but is 0.148. So it's, sorry about that. And so what we have to do is just calculate this. And we will get a value which is 59.9, or if you want to round it up to 60, you can do that if you want to. And the unit is 60 gram per mole. Oh, and guys, feel free to do the calculations with me as we go along, yeah. And finally, we need to determine the molecular formula of A. Basically, for the molecular formula is a constant N multiplied by the empirical formula. How do we get the N? The N is the MR of the molecular formula divided by the MR of the empirical formula. And for the MR, we get a value of 60, right? And for the empirical formula is CH2O3. All we need to do is just sum up the AR, which is 12 plus 2 plus 3 times 16. 3 times 16, that's 48. 48 plus 2, that's 50. And so, wait, 12 plus 2 plus 3 times, I don't want to get the calculations wrong. So this is 60 over 62. And if we were to round up this value, we will get a value of 1. Then, hence, your molecular formula is the same as your empirical formula, and it's CH2O3. Okay, so we're done with problem number 1. And are there any questions so far? No? Okay. If there's no question, I'll just move on. And so, yeah, the second problem is quite straightforward. Instead of dealing with gas or something like that, this time we're dealing with liquid. And since we're dealing with liquid, we are dealing with a value known as concentration. And if you read the problem, the concentration of a solution is the amount of moles of the solute per unit volume of its solvent. So basically, the concentration, C, is the amount of moles divided by volume. And when you do problems in chemistry, you're bound to meet a unit known as molar, M, 1 molar. And this molar is equivalent to 1 mole per dm cube, right? And so, and then this is the unit, yeah. Oh, and before I forgot, 1 dm cube is the same as 1 liter. So that's the conversion, yeah, that you need to remember. And so for problem A, calculate the amount of moles of NaOH in a 250 milli solution of that much. So what we need to do is we are told the concentration and the volume. However, this volume is in milli. We need to convert to liters first. So this will be 0.25 liters. Yep. So let me check the. Oh, guys, I'm also looking at the chat just in case there's somebody who wants to ask me something. So if you're uncomfortable with speaking out the question, just type it in the chat and I'll answer it later. Okay. And now for the amount of moles, we're going to use this formula, which is N equals to CV. For the concentration, we are told that it's 0.05. And for the volume, we are told it's 0.25 liters or 250 mils. And we get a value of 0.0125 moles. And so that's how we do the first problem. Okay, and so ignore problem C. Okay, there's nothing to see there. And for the next question is the concentration of ammonia when 17 grams of ammonia is dissolved in 100 liters of water. Okay, so basically for this problem, we are told the mass, but we need the mole. So all we need to do is just convert the ammonia into moles. So that means we need to find the MR of NH3, which is the AR of N is 14, the AR of H is 1. So that means this is 14 plus 3 equals to 17. Hence, you have a mole of ammonia of 17 over 17, which is 1, a beautiful number. And hence, your concentration, and this is how we write concentration, guys, so don't be surprised when you see a notation like this. This means concentration of ammonia. We put it in a bracket that looks like this. Hence, the value is 1 over 100 is 0.01 molars. Okay, now we get to the second problem, which is a dilution problem in which we need to prepare 200 milliliters of 0.1 molar HCl solution from a more concentrated solution, which is 0.2 molars HCl. And since it's dilution, when we dilute something means we add water to it. So when we add water to it, so that means the amount of HCl or the amount of moles of HCl will remain constant. So that means N1 will be equivalent to N2, and we know the formula of N, which is C times V. And so this will be C1 V1 equals to C2 V2. All we have to do is just input the value now. And guys, bear in mind, since this is a ratio problem, we don't need to convert the units of the milliliters and so on and so forth. So it's very straightforward and trivial. So this is what we need to do. To V2. And so we get a value of V2, which is 100 millis. Benar nggak tuh? 0,2. 100. Yep, it's correct, 100 millis. And so what would you need to do? First of all, if let's say you are entering into the lab and the assistant or whatever module that you have will ask you to prepare this much solution of HCl. So what you should do is take 100 milli. Okay, I'll just write down first. Take 100 milli of the 0.2 molar HCl, add water until 200 milli. So that's what you should do. Okay, so now we're done with the stoichiometry part. And if there's anything that, and again, I would like to press this again, if there's anything that you would like to clarify, just raise your hand, okay? And so now we're going to deal with problem 1. And so problem 1 is about equilibrium, in which Henry is given an assignment on chemical equilibrium by his chemistry instructor, and he is he is asked to answer questions on the factors that affect the equilibrium of reaction as well as its appropriate calculations. And so, as a good friend, please explain to him what equilibrium means, the main principle involved, the factors that affect the equilibrium position, and the calculation process. And so for this one, it's actually very straightforward. First of all, we need to explain to him what equilibrium means. So equilibrium is when the rate or how fast the forward reaction, how fast a reaction goes, and equilibrium is the rate of forward equation for forward reaction is equal to the rate of the reverse reaction. And when we're dealing with equilibrium, we're dealing with reactions that go both ways. Meaning, hence you will see a sign that looks like this. This sign is used to indicate something that is going back and forth. Right, and so next, let's continue on with the problem. Describe what the main principle is. So the main principle is known as Le Chatelier's principle. What is Le Chatelier's principle? So basically, according to this guy called Le Chatelier, is that when a change is introduced to a system, the system will try to revert to its original state. So this is basically a simple definition of Le Chatelier's principle. For a more accurate one, you can go consult your textbook, or you can go consult any trustable internet sources. And so next, since we now understand the principles involved, we can try explain the factors that affect the equilibrium. Basically, there are a few factors that affect the equilibrium. The first one would be the concentration of the reactants product. So what I mean by this is that if we add the concentration of reactants, meaning we are adding a reactant here. So in order to we are introducing an addition into the reactant. So that means the system will do whatever it can to revert it to its original state. So that means this reaction will shift to product side. And vice versa occurs. So basically, let's say if I take some of the reactants, that means the product will dissociate to form the reactants again in order to increase the concentration of the reactants. Next would be the pressure, and simultaneously as well the volume. And bear in mind, this is for gases. And in order to understand this one, we need to take a look at reaction, because this type of equilibrium will take place at a case-by-case basis. And so, let's say I have a reaction like this, your ammonium production, or commonly known as the Haber process. And so, if we take a look here, all of this, if I forgot to tell you, all of this is gas, okay? This is gas. So let's say I increase the pressure. That means the system will try to reduce the pressure by shifting to the side with the lowest sum of coefficients. So in this side, there are 4 molecules. 3 plus 1 is 4. For this one, we have 2 molecules. So since this is the side with the molecules, so for this equation, if we increase the pressure, that means this will shift to the product sides. means more NH3 formed. And as I said before, this is at a case-by-case basis. So just try and analyze the system by identifying which side has the same number of moles, has the greatest number of moles. Then you can analyze the pressure, the changes in pressure. And for this one, for volume, let's say we increase the pressure, that because we know that pressure is inversely proportional to volume. So that means if we decrease the volume, the same thing will happen when we increase the pressure. And yeah. Oh yeah, now I want to ask one more thing. What else will accept? What about this thing known as catalyst? Will it affect the position of the equilibrium? Kira-kira iya atau enggak? Anyone can answer?
Enggak, Kak.
No, right? Okay, good. Catalyst, the function of the catalyst is to increase the speed of the reaction. So that means this catalyst here will not affect the reaction, the equilibrium position whatsoever. Okay, so that means catalyst, we're going to delete that. Oh, and before I forget, the final most important one is temperature. This one is for reactions that involves heat, or in simpler terms, we have two types of reaction in chemistry that involves heat, which is exothermic and endothermic reactions. This one releases heat, and this one absorbs heat. Wait, let me just... You haven't got this material yet, but then I think in the near future, your lecturer will give you something like this. The reason why I have to teach you this now, or else you won't understand the concept I'm going to give you, which is the applications in the acid base. Okay, now let's continue. The calculations next. Now we're done with the factors. Now we're going to do with the calculations. And to make it simple, I'm going to use the same equation, which is this. So we have two types of equilibrium constants that we need to calculate. The first one would be Kc, which it is based on concentration. The second one is Kp, where it's based on pressure. Or to be more specific, the partial pressure of each of the gaseous reactants. Because all of this is gas, and so that means all of this would affect the reaction. And bear in mind, the reactants and products that we involve in the calculation of Kc and Kp must be both in aqueous or gas. Liquid or solid state will not affect the value of Kc or Kp. And on a side note, for Kp, it will only affect the reactants that are gas, because the only thing that can exert pressure is gas, right? Not liquid, not aqueous or whatever. It's gas. So that means this one is for gases only. This one is for all. Okay, so how do we write the equation? First of all, we always take a look at the reactant, at the product side, sorry, the product side. And so this is the concentration of ammonia. Look at the coefficient of ammonia is 2, and so we raise this to the power of 2. And hence, we do the same here in the bottom one, which is N2 concentration of nitrogen times with the concentration of hydrogen raised to the power of 3. Okay. Next would be the value of Kp. And as I've said before, the value of Kp depends on the partial pressures of NH of nitrogen of the gaseous reactants. And since all of this is gas, hence all of it is involved. So we have PNH3, PN2, and PH2. And again, we look at the coefficients. We square this, we raise to the power of 3, and we leave this as it is. right? And if you have, I don't know if you've known this already, but Kp and Kc, they have a relationship, and Kp is equivalent to Kc multiplied by RT delta n. What's delta n? Delta n is the difference in the sum of coefficients. So I don't know where I should write this. Just and so delta n, just where's the sum of coef of product minus sum of coef of reactants. Okay. Right. And so this is all you need to know for equilibrium, but I already prepared a problem actually for you for us to discuss together. However, I will have to leave that to you because we are running out of time. So I leave my line in the description, in the chat, sorry, description. In the chat. This is my line. Feel free to contact me at any working hour or when I'm free, and if you have any questions regarding with basic chemistry. Okay. And I'll do my best to answer. Okay, so now we're going to skip this one because or else we won't have enough time. Okay, now the next part is talking about acids and bases, and this is the core of one of the cores of chemistry. And there's a saying that if you master this part of the course, which is acids and bases, you can understand we can understand reactions that are involving, let's say, organic reactions. Oh yeah, for text, okay, someone just asked me about the textbooks. For the textbook, I'll just give it in the chat, or it is Raymond Chang. Basically, any textbook that you have will do. So you are, especially that now you are university students, so do not expect your quote-unquote lecturers to spoon feed you. So you have to find out your own information. So this is the textbook, 10th edition chemistry. So that's one of the main resources that we use, and I think I can show you. This is what the book looks like. I don't know if you can have a look. So that's what the book looks like. And so yeah. Right. Oh, as I was saying, the first problem involves 3 different definitions of acids. And so for acid definitions, you have 3 definitions, which is Arrhenius, Ronstadt-Lowry, and Lewis. For Arrhenius, acid is a substance that dissociates. I'll just rush through this one. So I think we'll be able to finish at around 9:30. So that's 9:30, that's the max. Okay. Substance that dissociates to give H plus ions. Ini ada pertanyaan lagi, Kak, tadi Kc itu bisa buat semua jenis zat atau cuma liquid ya? Nah, tanya gini, Kc tadi itu hanya untuk dalam kondisi aqueous state. Kan kalian di kimia kan ada 4 state kan, ada solid, aqueous, liquid, sama gas. For Kc itu cuman buat dalam state aqueous sama gas. Itu. Ya. Don't forget these two. Ya. Ya. Aqueous and gas sudah. Liquid nggak bisa. So basically, kalau misalnya di reactionnya tiba-tiba ada menghasilkan air, that water will not be part of the Kc calculation. So I hope that answers the question. And oh yeah, guys, if you read through the textbook and find any explanation that I give is different, then you follow the textbook, yeah. Because I'm only human, so I can make mistakes as well. Next, if H plus ions, the Bronsted-Lowry is a substance, acid is a substance that, or to make it simple, to save time, as according to Bronsted-Lowry, acids are proton donors, meaning they donate proton. And guys, in some instances, or in some books, they say protons may refer to H plus, so don't get confused. For Lewis, since we see that this one is the acid is giving something, but for Lewis, the acid receives lone pair of electrons from other compounds. And so these are the three definitions of acids that you have. It also applies to base, but for base, I think I should take a note here. For base, ini OH minus, ini base proton acceptor, ini base proton lone pair receiver. Yeah. Okay. Next is to give the classifications of acids based on the strength. And so this will be very simple and straightforward, just like the first one. First, we have two types of acid strength. Very simple, strong, weak. Strong and weak. This one dissociates completely to give H plus ions. This one dissociates partially to give plus ions. And also take note for weak and also the classifications. This one is HCl, H2SO4, HNO3, and many more that you can find. If I remember, there's seven of them in total. And for weak, these are all carboxylic acids. Later, when you get the course of organic chemistry for chemical engineering students, I don't know if metal dapat atau enggak, but all carboxylic acids are weak acids. Yeah. And next, we calculate the pH of 0.1 molar of HCl. And for the calculations of acid, we have this formula for pH is negative log H plus concentration. And this applies to all. And we also have this thing known as POH, which is negative log OH minus. And we know that the greatest number in the pH scale is 14, and this is actually an addition of pH plus POH. So remember these three formulas when you are calculating pH, and it applies to all forms of acids and bases. Right. And so for this one, and since HCl is a strong acid, this is how we calculate the H plus. Look at the H. How many H's are there? 1, right? And so 1 times 0.1, you get 0.1 molars. That's the concentration of the acid. Hence, let me just. So pH is negative log 0.1, and we get, and if you input this into the calculator, you'll get 1. Yeah. Oh, and guys, just if you know the pH scale, so this is 0, 14, 7. This is neutral. This is basic. This region here is acid. And if you divide it again, this is strong, weak, weak, strong. Okay, I think I'll just erase this for now. Oh, and guys, I would like to rephrase this again. If there's anything that is unclear, interject me at any point, then I'll answer your question. Okay. Right. And so, as I said before, the carboxylic acid are weak acids. Acetic acid is not a strong acid, it's a weak acid. This is a carboxylic acid that comes in this form. So yeah. And in order to calculate the H plus concentration, they have their own formula, which is H plus equals to the square root of Ka times M, or the concentration of the acid. And so this is square root of 1.3 10 times the power of -5 times 0.02. And hence, if you put this into the calculator, you'll get the H plus value. Once you get the H plus value, plug it into pH equals negative log H plus concentration, you'll get the pH. But then I won't calculate here just to save time. And next is we're going to calculate the pH of a base. And barium hydroxide is a strong base. So we have to calculate first the OH minus concentration, which is, if you look at the number of OH ions, there's 2 of them. So 2 times 0.3, that's 0.6. And all to do is put it into this equation. You will get, I think 1 minus log 6 with 6 kali 10 pangkat min 1, pisahin min 6 log 1. Yep, you'll get a value of 1 minus log 6. Okay. And for the pH, and since we have the value of pOH, to find the pH, we just plug it into this equation, 14 minus pOH. We'll get instead we'll get 13 plus log 6. Okay, so for now, do we have any questions before I move on to the next part? None? Okay. Okay, right. For this time, we are asked to derive an equation. So this is fully mathematics. So yeah, just bear with me for a while. First, we're asked to derive an equation for Ka. And remember that this Ka is actually an equilibrium constant, which is why I had to teach you equilibrium in the first place, that you'll understand this. All right, right. I forgot something. Yeah, thank you for that question. If you go back previously, this is for strong base, right? And this is the formula for weak base. As for weak acid, for weak base, we have this formula. I think I forgot to mention it. Yeah, so thank you, I think, for someone for reminding me. So this is the formula that for weak base, which is Kb. But let me check something first. Someone just messaged me, give me a moment. Okay. Anyway, let's go. Moving on. As I said before, the Ka is an equilibrium constant. So that means this Ka is, so let's say I have an equation like this. This is a weak acid, right? So that means it will dissociate to give something like this. Sorry. H plus A minus. Right. And so for the Ka, we just apply what we know just now, which is, yeah, hello, ada yang mau nanya? Oh, okay, I think I must be doing this. Over HA. And that is your equilibrium constant. Okay, so next, is to find the pH in which weak acid is reacted with a strong base, and to give the official name for the equation and type of solution it forms. So basically, this is a segue into the next part, which is buffer systems. And so the name of the solution is a buffer solution.
Recording in progress.
And it's a buffer solution. Right? Can somebody mute? Because okay, it's a buffer solution, as I stated before. And the official name of the equation is called the Henderson-Hasselbalch. I don't know if that's how you pronounce it. Equation. And in order to derive this equation, we take a look at the previous one, which is Ka equals to H plus A minus over HA. Now, what do we do next is we want the formula of pH, right? And we know that pH is negative log H plus. So we make H plus the subject of the equation, which is Ka HA over A minus. And all you have to do next is put negative log on both sides. Sorry for writing it like this, so because in order to conserve space. And so we get pH equals to negative log Ka minus log HA over A minus. Right? So pH is pKa minus log HA over A minus. Yeah. And so this is the equation that you will get to calculate for buffers. Okay, so now let's apply the formula here. And so for pH, and the ratio of the red form to purple form is 2:3. So that means this red form is your HA, and your purple form is your A minus. And so pH equals pKa minus log HA over A minus. We know the pH is 5, so this is 5 pKa minus log 2/3, right? And so pKa is 5 plus log 2/3, and if you do the math, the Ka is 10 to the power of -5 minus log 2/3. And so if you put into the calculator, you'll get some values, but which I'll leave you to do. And I think we need the Ka for the next part. Okay, so sorry, I think I have to calculate this, which is, wait. So I think it's Ka is 1.5 times 10 to the power of -5. 10 pangkat. Yep. So if I make any mistakes in calculations, please tell me so I can correct it. Okay, so that means now. Oh, and guys, because in my prediction is that we don't have enough time for this, so I'll send the document here, the one with the annotations and without the annotations, to a representative, and then also the solutions to the problem. Okay, so don't worry about it. Okay, next. Okay, so we have a new equilibrium system, so we have to calculate the value of Ka. So all you have to do is get the value of Ka. Wait, let me check something first. Okay. And as I've mentioned before, H2O is not involved if we're dealing with concentrations. So yeah, this will be the formula. And now pay attention to this sentence. The intensity of the red color decreases by tenfold the initial intensity. Ngerti nggak maksudnya apa? So that means the intensity of the red color, this one, decreases by 10. So let's say this concentration is A. At equilibrium, it will be A over 10. That's what it means. Okay. And so we have the concentration of CYH plus, which is A over 10 at equilibrium. And because of that, this one is at equi, so that means this is A over 10. At SO2, this is 0.05. Now we just need this concentration. We have the H plus concentration, which is 10 to the power of -5, right? From the pH. So in order to do this, we are actually given a clue that the color of the red color decreases by tenfold. So that means from a very, very red color, you get something that is semi colorless. So that means this concentration increases. And does it increase by tenfold? No. So this is initial, right? A at equilibrium is A over 10. So that means react would be A minus A over 10, 9A over 10. So the concentration of CySO2H2 is 9A over 10. So this is 9A over 10 over 0.05 times 10 to the power of -5 A over 10. And if you were to calculate that value, we can cross out A over 10, by the way. And you will get 1.8 times 10 to the power of -3. So that's the value that you will get. Okay, moving on. This one is about titration graphs. But unfortunately, I don't think we'll be able to do this problem as well. But then I'll skip this because this is important. So I'll skip this for a while and move on to the next one, which is about the reaction of metals. And for this one, I'll just keep it simple. And I'll just give you the answers directly. And so first of all, sodium is a metal in the first group of the periodic table as a group 1 metal. Sodium has its own characteristics and is unique when compared to elements in other groups. This can be seen by how each of the compounds behave in different conditions. So basically, if you look at your periodic table, I think I have it here. You look at your periodic table, and if you go through from this side, from this side to this side, each of them have their own unique reactions and capabilities and the way it behaves. And so for question 1, we are asked to compare the reactions of NaCl and SiCl4 when it reacts with water. Okay, so first we'll start with the NaCl. So can anybody tell me what will happen if I put NaCl in water? Will it react or what? What will happen? Anybody turn on their mic and give an answer? It's okay, don't be shy. It's okay. And this class is it's an open class, so you can give any answer that you want without the fear of being harassed or bullied or whatsoever. Okay, seems all of you are still shy. So that means if we were to dissolve the NaCl in water, it will not react at all. It will just dissolve. So this is dissolves. And for the SiCl4, what will happen to it? For this one, it will react to form SiO2 plus 4HCl. So this is 2. Okay. And this is something that might be very new to you. I'm not expecting you to get this correct or to understand this, but for now, this is the reaction of it. And when we're studying about reaction of metals, it's something, in my view, is something that is half you can understand, half you need to memorize. So yeah, it involves a bit of memorizing here. Explain in terms of their bonding and structure why this is so. So we know that NaCl is ionic. This one, the SiCl4, is simple covalent, right? And this NaCl4, it has a giant lattice structure. If you want to Google it, go ahead if you want. Okay, so another question is, why does NaCl4 NaCl does not react with H2O, but reacts with SiCl4? I was about to get to the explanation. And so basically, if we dissolve NaCl4 in water, the bonding here in NaCl is strong, which is why it doesn't react with the water. That's the simple explanation. For the complex explanation, I cannot give it to you now because it's a bit long. And for the 2H2O and the SiCl4, this one is a simple covalent structure, which means the bonding here is weak. So which is why this SiCl4 can dissociate, meaning it can break apart its atoms and react with water to form SiO2 or silicon dioxide. And this silicon dioxide is a special compound that perhaps you can learn about. Okay, moving on. Describe what you see when sodium is burned in chlorine. Well, this one is also memorization. So first of all, we can answer this in 2 different perspectives. Versus the perspective of the sodium, which is so let's say we burn sodium in the lab. So what color will we see? We'll see, like, I think a yellowish color, right? And also, if when we burn sodium in chlorine, because there's this big energy that allows the sodium to react with the chlorine given by the heat, hence the reaction is like this. And we have the formation of NaCl, which is solid. And this NaCl, it's a white solid, right? If you look at your table salt, what color is it? It's white, right? And so we can see formation of white solid. And next, for chlorine, because the amount of chlorine decreases as the sodium is reacted, we can see that there's a decoloration of chlorine. Okay, so moving on, and I'm sorry for the handwriting is bad because I'm using something like this. So yeah. Next is that aluminum is an example of metal, right? First, we need to describe the structure of solid aluminum. Basically, we are asked here to describe what is known as metallic bonding, because aluminum is a metal, hence this metal will exist a special type of bonding known as metallic bonding. And first of all, we describe the arrangement of aluminum is that the aluminum has regular or arranged arrangement. So, or it exists as a lattice. You can Google it right now if you have your phones with you, and so that you can see what it looks like. So it has a regular arrangement in a lattice, but a lattice of what? Or rather, what makes up the lattice is the positive ions or the cations. And for chemical engineering students, I think in semester 3 you'll get a course called Material Science and Corrosion. So you'll learn about this as well, metallic bonding. And next is that it is, and because an atom of aluminum has both positive ions and also negative ions holding them together. Hence, we have this thing known as a sea surrounded by a quote unquote sea of electrons, or quote unquote delocalized electrons. Or to put it in simple terms, these are called free mobile electrons, meaning these electrons are free to move in any direction, which is why your aluminum can act as a wire. Makanya kabel aluminium kalian itu bisa dipakai buat aluminium itu bisa dipakai buat kabel atau dan lain-lain. And basically, if you use aluminum as one of the cathodes in an electrolytic cell, it will be able to deliver the electricity. Ya gitu. As an example. Apalagi, yeah, that's why it's suited for electric wires. Electrons allows electricity to freely flow through. Now for number 4, the aluminum reacts with chlorine to form a white solid chloride, and it sublimes or it undergoes sublimation. And we need to describe the structure and bonding in this compound and suggest how it explains the low sublimation temperature. Okay, so for the low sublimation temperature, first of all, we need to understand what type of compound it forms. And I don't blame you if you, for the first time, if you think that the compound form is AlCl3. But actually, no, this is not the one formed. But instead, the one formed is this Al2Cl6. This type of compound undergoes a reaction known as dimerization or something like that. And this is covalent. And as usual, we can see that the covalent bond can be a weak bond, which means that we have weak intermolecular forces. And if we have weak intermolecular forces, it means that less energy is needed to, less energy is needed to break the bond. Yeah. Because of this, less energy needed to break the bond. To not break the bond, sorry, to overcome the intermolecular forces. And so finally is the acid-base behavior of the oxides in the third period. And to describe the structure and the bonding of sodium oxide and aluminum oxide and sulfur trioxide. Okay, so now we'll start with the bonding first present. We know that Na2O, this one is ionic, L2O3 is ionic, SO3 is covalent. Okay. Wait, let me just erase this because it's going to be complicated if I make it like this. Describe the structure and bonding of sodium oxide. And yeah, and for your information, metals that are in group 1 and group 2, they tend to be basic. And for aluminum oxide, this is special because it's known as amphoteric substance, which means it can react with both acids and bases, which you will see later when I write down the reactions. For SO3, this is acidic, which is why if you react this further in the environment, it will form, I think, sulfuric acid. Yeah. And next, we're going to get into the reactions. First of all, we'll focus with Na2O. And because it's basic, we're not going to react it with another base, but instead with an acid like HCl. We're going to get NaCl plus H2O. Okay. Okay, so now we're done. Now we're going to move on. It's simple as this, so you don't have to. And for Al2O3, as I've said before, it can react with both acids and bases. So if you react to this, we will get six. So this is the reaction. Now for SO3, this is basic, so we're going to react it with acid. Sorry, this is acidic, so we're going to react it with base. Sorry. So this is NaOH. So we can get NaHSO4, or if you react it further, okay, SO3 to NaOH, you will get Na2SO4 and water. So these are the behaviors of the compounds. And for Al2O3, as I've said before, its amphoteric can react with both acids and bases. Hence, we have Al2O3 plus NaOH to get a substance known as sodium aluminate, or NaAlOH4. Okay, so these are all the reactions that we need to do. And next, this is the final, I think, yeah, is it? Yeah, it's the final part of the problem that we have, which is electrochemistry. And first of all, this is one of the applications of electrochemistry, which is electroplating. Yeah. So basically, when you take a metal and you coat it with something else, with another metal, let's say, which you will see here. And the case that we have here is the case of plastic, where we are going to electroplate, quote unquote, plastic with chromium. First of all, we need to explain why the plastic is coated with the graphite paste. And as we know, graphite is an electrical conductor, while plastic is an insulator, meaning it cannot conduct electricity. So in order to displace the metal on the plastic, we can, okay, so in order to displace the metal in the plastic, what we need to do is to displace the metal on the plastic, we need a conductor so that the metal will come, so that the electricity can flow and the metals ions can come flowing to the plastic. And so that's the explanation. Graphite needed allow. Okay, so I won't bother you with this for a while. So in order for the cell to work, what electrode must be placed so that the circuit will be complete? Chromium. Because we're going to use chromium as the solution, and we're going to put chromium on the what we call the plastic. So hence we need a chromium electrode. And for this one, next, we're going to draw the circuit. Okay. So this is what the circuit will look like. So let's say this is what tub containing Cr3 plus ions. You have the power source. And so this one is your Cr metal. And this one is your plastic. What's the difference between plus and minus? Your minus here is your cathode, where reduction takes place. And your positive here is your anode, where oxidation takes place. Okay, in order to make it quick, I'll just skip through this one. And explain the theory involved in this process. This is known as an electrolysis cell, where electricity is used as an energy source to start the reaction. So that means the reaction that occurs here is not spontaneous. We need the electricity to give the energy, right? Yeah, let me just save this for a while. Give me a moment. Okay. And the next part is that a man wants to decorate the car with chromium ions. And so for this, we need reactions that takes place in the anode, cathode, and overall. And for the anode, it's mentioned here that there's oxidation of water, and so water is involved. And guys, make sure you pay attention at this part, because this is one of the most important reactions in chemistry, which is to make oxidation reactions that are done under certain conditions, let's say acidic conditions. So first of all, we take a look at the ions on, the atoms on both sides. So what is missing? H here is missing, right? First of all, we look at the number of atoms here that are missing. So we have 2 oxygen atoms. Here we have only 1, hence we need to multiply this by 2. Okay, next, we need to add with the number of the H plus ions here in order to balance the hydrogen. So this is H plus 4H plus. Hence, for this one, we get, in order to balance the charge, next we add 4 electrons so that it will be neutral on both sides. So that's the reaction in the cathode. So we have 10 minutes more, so I'll speed this up. So for the cathode, it's a special reaction involving chromium ions. So in the cathode, reduction happens, right? And so Cr2O72 minus this one, you will get Cr, right? And so because of this, first we balance the number of atoms. So this is, there are 2 Cr here, we need 2 Cr here. Next, we balance the amount of oxygen with water. So we have 7H2O, right? And so what we need to do next is to balance the hydrogen by adding H plus ions. So we add here 14H plus. Next, we balance the electrons by adding 12 electrons. So that's the process. And so for overall, in order to balance the overall, you have to take a look at the number of electrons because that's what we want to eliminate. There's 12 electrons here and there's 4 here. So that means in order to make this one 12, we multiply this by 3 and we multiply this by 1. And overall, we will get Cr2O7 2 minus plus 2H plus 2Cr plus H2O plus 3O2. And this is, I simplified this equation already. So if you want to do the entire thing, go ahead. And next, we draw the structure of Cr072. And the structure just looks like this. Sorry, wait. I think it's supposed to be Cr2O7, sorry. Cr2. So the structure looks like this. Sorry. I think there's here. So this is what Cr2O7 looks like. And for the clearer picture, I'll give you the drawing to this. Okay. And next is the calculations. So determine the amount of oxygen gas released. Okay. So the MR of chromium is, I think, 52 grams per mole. So first we need to find the mole of chromium, which is 104 divided by 52 equals to 2 moles of Cr. And for this one, we know that the reaction is, this is the reaction. So we have, in order to find the mole of oxygen, we need to multiply this by this by 3/2. Hence we get 3 mole O2. Okay, now we move on to the next part. And this one is involving the calculations. And so this is the formula that we use, which is mass equals to IT over NF M R, in which F is a constant known as the Faradays constant, which is 96,500. And so for the M, we just put 104 equals to 25 T over how many electrons are used? In here, the electrons used, there are, I think, 12, right? 12 electrons. So I'll get back to you on this. 96,500 divided by times 52. Okay, now we just need to get the value of T. I'll just be quick on this. And so the time needed would be 92640 seconds. Okay. So if you want to change it to, if you want to simplify it, go ahead. But I'm just going to leave it at that. And so this is the final problem that we have for tonight. And I'm going to be quick on this. And so this is a galvanic cell, which is in which the reaction occurs spontaneously, but then there are certain equations that occur here. Okay, first of all, we need to write the half reactions of each cell. And in order to identify which one is the half cell, we need to know the value of the Cu. And so because Cu tends to be at the bottom, wait, sorry. Sorry, here it says here, palladium acts as the positive pole. That means you're given the clue and the positive pole here is your cathode, and yeah, there's a reversal of the signs, but then reduction still occurs. And for this one, and so at the cathode, we have a reduction of PD 2 plus to become PD plus 2E. That's the one in the cathode. This one is in the anode, means we have an oxidation of copper. So that means this is what the reaction will look like. Right. And so we are not asked to write the overall reaction, so which is why we just leave it at that. And for this is to calculate the reduction potential of PD2 plus. And for to calculate that, we need this formula. E standard cell equals E standard cathode minus E standard anode. So yeah. Okay. And so we just need to plug in the equation. So this is A609 equals to E cathode. Anode is this one, right? So that means E cathode minus 0.304. You will get E equals to positive 0.913 volts. That's the value that you get. And next, oh yeah, before I forgot to tell you, this is called the standard cell potential. By standard meaning, this is measured under standard conditions, which is 25 degrees Celsius and 1 bar. So I'll just write this down here. At 25 degrees Celsius, 1. This is what 1 at, I'm sorry. This is standard conditions. And also this is supposed to, for standard, this is 1 molar. This is 1 molar. Okay. And now let's go on. Right. So in order to calculate the cell, which is not under standard conditions, we use a special equation known as the Nernst equation, in which E to negative E cell minus 0.0592 over n log Cu. Yep. Cu over PD plus. PD2 plus. So PD2 plus. Okay. And if you were to plug in the values, I'm not going to write it again. So for the n, since there are 2 electrons, so that means n equals 2. Hence, we will get, you just plug in the values and you're going to get the answer. So that means it will be 0.609 equals to minus 0.0592 over 2 log 2 over 1. And so just plug in the calculator, you're going to get that value. And to calculate the Gibbs free energy, we have an equation called delta G equals NFE. For Gibbs free energy, you don't have to know what this is yet, but then if you study electrochemistry later, you're going to know what this is. So I'm not going to explain it to you now. And so this is negative 2 times 500 times 0.609. When you study thermochemistry, you're going to know what Gibbs free energy is. Okay. And yeah, that's the final part of the equation. You just need to put that in the calculator. And finally, this is the use of the salt bridge. Basically, the salt bridge, even though it's just there for, this salt bridge has a special function. The function is to prevent charge build-up. Because as reaction progresses, dikit lagi ya guys, as reaction progresses, the amount of ions will build up. And if this build up continues, it will cause the cell to break down and not function properly. And so the salt bridge prevents build up by neutralizing the excess charge. Okay, so name another compound. Okay guys, so rumus yang nomor 3 itu apa? Itu Nernst equation. Jadi kalau misalnya kalian lihat di textbook, coba cari Nernst equation ini. Sorry, ini tulisannya nggak terlalu bagus karena ini writing pad-nya. So this is E cell, E standard cell minus 0.0592 over N log Q. This is the general formula, okay? This Q is your equilibrium constant. Makanya gua ajarin equilibrium tadi. Sekalian. And for this case, your equilibrium constant is Cu2 plus Pd2 plus. Okay, so for now, so that's all for tonight's assistance. So before you leave, is there any questions that you would like to, or any issues that you would like to have addressed? I'll wait for 10 seconds.
Kau boleh minta file ininya nggak, Kak?
Of course, I'll share this later. And ini kan karena tulisannya kan agak acak-acakan kan, because of my writing pad. Jadi I'll give you the one yang benar-benar pristine, kosong, as well as the answer key. Yeah, don't worry. That's my promise to you.
Oke, makasih, Kak.
Nah nanti recording, kalau recording itu minta I'll talk to Rayan about this. I think we recorded the meeting, right? And I think it's still being recorded until now, right? Okay. Anything else? Kalau nggak ada, aku stop share. Okay guys, karena ini bagian dari Acro, so I'm going to stop recording.